Hello everyone. In this second lecture on frictional plasticity, we will discuss faulting and tectonics. Last week, we briefly introduced the problematic of faulting in the Earth crust, and I recall you this famous example of the Glarus frost in the Swiss Alps, where you see the manifestation of a very sharp fault zone that accumulates a lot of strain that allowed to emplace old rocks onto younger rock units. Then we've expressed the Moore circle. For this, we had to learn how to project a 2D or a 3D stress state into arbitrary coordinate system, a transform coordinate system. And this allowed us to construct this type of representation where you have the normal stress on the x-axis, the shear stress on the y-axis. The circle represents the state of stress for different angles of the rotation of the coordinate system. If the shear stresses are 0, we are exactly along this line. We will have two values. This will be the principal stresses. This is for a coordinate system in which the shear stress vanish. But in the general case, we can be along with any orientation here to theta. And for this, the stress tensor has shear components, which are non-zero. They are maximized here. These are the formula that you derived in the exercise. We've also introduced Byerly's law. So Byerly's law shows you the result. It's a result of a regression through a data set. And these data sets are points in the normal stress shear stress diagram for which rock yielding takes place. There is a law that can be fitted, and the law is luckily a linear relationship. The shear stress is equal to a reference intercept value tau 0 minus tangent phi, that is the slope, times sigma. The minus sign is because here it's actually a negative normal stress that is represented. So for an intact rock, the cohesion is about 50 megapascal, and the friction angle is about 30 to 35 degrees. So let's first discuss the fault angles using these two tools that were introduced previously, which are the Moore circle and the Byerly criteria. So we always work in this space where the normal stress is along the x-axis and the shear stress is along the y-axis. So you see a representation of the Byerly criteria. The angle of friction is here. Tau 0 is the cohesion there. And now we have a stress state represented by the circle here. Along the x-axis, we have sigma 1 and sigma 2. These are the two principal values, which are the values of the diagonal of the stress tensor in the orientation where shear stresses vanishes. So the question here is how to determine the fault angle relative to sigma 1. So you can imagine we have tectonic systems, and in a tectonic system, there's a sigma 1 acting in a direction, and we want to predict at which angle from sigma 1 a fault is going to develop. We can use this construction here to determine that angle. So I will introduce the angle to theta and the angle of the fault. So I go back to this sketch here, and you will see theta is the angle of that plane. That is the value of theta. And here we have 2 theta. That plane is nothing else than the normal to the fault plane. So when we will compute the angle of the fault relative to sigma 1, we will measure 90 degrees minus theta. So how to do this now, we will use the sum of the angles of a triangle. We know it's equal to 180 degrees. So let's draw the AFB triangle. We have the angle phi on that side, and there is a right angle there. So let's make the sum of these angles. So we have phi plus 90 degrees plus that angle. That angle is 180 degrees minus 2 theta. 180 minus 2 theta. One can obtain phi is 2 theta minus 90 degrees, and hence we can solve for theta, which is phi divided by 2 plus 45. So that would be the orientation of theta. To compute the fault angle, we take 90 degrees minus theta. So 90 degrees minus theta is 45 degrees minus phi divided by 2. So that's how to compute the angle of the fault. Now let's make two examples. One example where the friction angle is set to 0, and one example where the friction angle is larger than 0. So in that example, if the friction angle is equal to 0, the fault angle will be 45 degrees minus 0 divided by 2. So the fault zone will develop at 45 degrees from the direction of sigma 1. That's if there is no internal friction. That is plasticity without friction. If the model has friction or plasticity, for example, in the case of Bayer-Lees, the angle is larger than 0, and rather on the angle on the value of 35 degrees, one can deduce the fault angle relative to sigma 1. So if you compute, for example, phi divided by 2, 45 minus phi divided by 2, you will obtain angles of fault relative to sigma 1 that range between 22 degrees and 32 degrees, depending on the magnitude of phi. So phi determines the angle of the fault relative to sigma 1. Now, let's establish a relationship between sigma d, the differential stress, sigma m, the mean stress, and phi, the internal friction of angle. So that's a simplified diagram here, where you have the shear stress again in y, and the sigma, the normal stress, in the x-axis. We assume that tau 0 is 0, so the intercept of Bayer-Lees law is at 0 here. Our Mohr circle is touching the line of rupture, and the angle is facing here. The opposed face to this angle is the radius of the circle, so differential stress divided by 2. And this edge has a length of sigma m. That's the position or the shift of the circle center. So if we assume tau 0, it means there is no tau 0 equals 0, there is no cohesion. The sliding on the fault only depends on sigma m. So we use now the trigonometric relation. The sinus of the angle phi is the ratio of this length divided by that length. So one can express, for example, sigma d divided by 2 is sigma m times sinus phi. So this little relationship, we have to keep it in mind because we use it a bit later in the course. Now, let's talk about the vertical stress in the crust. And we also introduced the concept of lithostatic pressure. So that's a slab of rock. We have the y-axis pointing upwards, and we have sigma v that we will represent here. So the vertical stress will be proportional to the load of the overburden of rock. So it's simply rho g y. As a convention, we assume that the stress is negative under compression here. So we introduce now the lithostatic pressure. The convention we use is that the pressure is positive in compression, for the stress is negative. So you will have different signs here. So sigma v is rho gy, and PL will be minus rho gy. So remember the definition of pressure from the previous lectures. The pressure is 1/3 of sigma xx plus sigma yy plus sigma zz. This is the trace of the diagonal of the stress tensor in 3D. In the static case, it is assumed that the three normal stresses, sigma xx, yy, and zz, are equal to the lithostatic, to the vertical stress, which is the weight of the overburden, rho gy. So if we apply this to the formula of pressure, we can substitute 3 times the same, sigma zz plus sigma zz plus sigma zz divided by 1/3, and this will give you the value of lithostatic pressure, which is minus rho gy. So sigma v is rho gy, and pressure, lithostatic pressure, is minus rho gy. However, in the non-static case, which means we have tectonic deformation, the normal stresses are not equal. We cannot assume that they are equal, and we need a more circle to represent the stress state. So the stress state is represented by this half circle here, and sigma xx is different than sigma yy, different than sigma zz. The pressure is formulated with this statement from the previous, definition from the previous lecture, and this is not equal to minus rho gy. So now we will do one assumption, and we will assume that sigma zz, the out of plane stress, will be equal to the mean stress. So the mean stress is 1/3 of the three normal stresses. From this, one can solve that sigma zz is 1/2 of sigma xx plus sigma yy. Then we have this definition. Now, when sigma zz is equal to the mean stress, one can also define the pressure. The pressure is minus 1/2 of sigma xx plus sigma yy. It's minus mean stress. So we also keep these definitions under our hand for later use. Now, one question that arises, this you may all wonder, what is the effect of fluid flow? You know that the rocks in the crust are porous, and that there might be an interplay between fluid flow or fluid pressure and frictional plastic deformation. Of course there is, and for this I introduce Terzaghis effective stress principle. So now you have to think about a volume of rock. We zoom into the rock, we have some particles of soils or rock, and there are some pores, and the pores are full of water. That's water saturated, and the water is incompressible. It's an incompressible fluid. So when this rock is under stress, the solid particles will deform. They are a bit compressible, so we can deform the system, but the water cannot deform, so the pressure will increase, and this will have an effect. It will have the effect of reducing the effective normal stress. So what is the effective normal stress? It's basically the difference between the normal stress sigma 1, the principal stress here sigma 1, and the fluid pressure. The fluid pressure also has an effect on all normal stresses, so it will affect sigma 1, sigma 2, and sigma 3 in 3 dimensions. So here, for the case where we consider 2 normal stresses, we can write it like this. If we compute the differential stress using these effective stresses, what we obtain, sigma 1 bar minus sigma 2 bar is simply sigma 1 minus sigma 2. So fluid pressure here disappears from this equation. In other words, fluid pressure has no effect on the differential stress. However, if we compute the mean stress now, we make sigma bar 1 plus sigma bar 2 divided by 2. We substitute the definition of sigma 1 bar and sigma 2 bar, and we obtain this relation, sigma 1 plus sigma 2 divided by 2 minus Pf. So this means that the fluid pressure has a strong effect on the mean stress, and this effect can be potentially large depending on the magnitude of the fluid pressure. So let's have a look now on the Moore diagram, and here it would be Byerly's law, for example. We have initially a circle with a given diameter and a given mean stress. If we increase a fluid pressure from 0 to a given value, the mean stress value will change, but not the differential stress. So the radius remains the same. So what fluid pressure does is that it will shift the circle towards the yielding line. So it can trigger frictional plastic deformation. So the Moore circle can shift the circle towards the failure line, and it does not increase the differential stress. It only affects the normal stress. So let's discuss now extensional and compressional tectonic regimes. So first we consider a slab of rock here. It is under extension. So what extension means? It means that the most compressive stress is vertical. So sigma 1 will be the vertical stress, sigma v, and it is equal to the vertical stress, so it's rho gy, as defined earlier. And we have horizontal stress, which will be smaller. It's applied to the site. Under compression, it's the opposite. So the vertical stress now is the smallest negative stress, sigma 3, and it is equal to rho gy. The most compressive stress is now horizontal, so it will come from tectonic motions, for example. And so sigma 1 is the horizontal stress. So sigma 1 vertical in extension, sigma 1 horizontal in compression. That's completely, these are completely different configuration. And remember the definition of the fault angle we derived earlier, 45 degrees minus phi divided by 2. This is the angle with regard to sigma 1 direction. So if you would assume that the friction angle is about 35 degrees, the fault should be at 28 degrees from sigma 1. So one would expect in compression to have, since sigma 1 is vertical, in extension, sorry, since sigma 1 is vertical, you would expect to have faults that are 62 degrees from the horizontal plane. However, in compression, the fault will still be at 28 degrees from sigma 1, but sigma 1 is horizontal, so one would expect to get a fault oriented at 28 degrees from the horizontal. This can be demonstrated by sandbox experiment. So you see here an apparatus from an experiment which was carried out in the 50s, and that's a sandbox. So these are this is sounds marked with passive markers of sound of a different color, and here is a piece of metal that can move to the left or to the right in order to either compress that side and extend the other side. So by moving this piece of metal to the right side, one can trigger compression in the right part, and you see the formation of tectonic naps and the formation of faults, thrust faults. And on the other end, the other side here is collapsing under extension because the plate is removed to the right side. So what we see basically is that if the plate is moving, sigma 1 is horizontal in that part of the sandbox, while sigma 1 is vertical in the other part of the sandbox. As the plate is moving, it's creating a bulge, so it's compressing a bit the right part, and the left part is already failing and making normal faults. And you see that the normal faults are indeed at about 63 degrees from the horizontal, as discussed earlier. If we keep on deforming this, you see the development of thrust faults, so that are making the nap boundaries, and these thrust faults in the compression regime are 28 degrees to the horizontal direction as earlier deduced. So this very basic experiment is a very nice demonstration of the different behaviors of the material under compression and extension. So it's very important to note that frictional material such as sand or crustal materials will behave differently in extension and compression. So why are extensional and compressional tectonic regimes so different? Let's go back to the Mohr circle and the Byerlee's law. So here's a circle represented for a compressional regime. So in the compressional regime, the principal stress, sigma 1, is the horizontal stress, so sigma h comp. The minimum stress is the vertical stress, and it's the lithostatic, the static load. The circle center is located here, minus p comp, or sigma min comp. So we can compute sigma d, the differential stress, and it's the difference between that value and that value. So it's sigma h comp minus rho gy. The pressure is minus sigma m, and it is equal to sigma h comp plus sigma v comp divided by 2. In other words, minus sigma h comp plus rho gy divided by 2. Under extension, we have the same vertical stress, it's rho gy, but in that case, this is sigma 1, and sigma 2, the minimum stress, is the horizontal one. So that changes things quite a bit, because if you compute the differential stress, it will be the difference between rho gy and sigma h x. And the pressure is minus sigma hx plus rho gy divided by 2. So for the same vertical load, we have different pressures and different strengths or differential stress. That's very important. So pressures and differential stress are different in compression and extension. Now, let's look at the depth dependence. So we have identified that stresses and pressure can be different in extension and compression. What is the effect of depth now? We draw the Mohr circle and the Byerlee line, this time assuming tau 0 equals 0. So again, we have a 0 intercept. The angle of internal friction is here. And we have a circle for compression. The center of the circle is here. The radius is there. And here is a right angle. So we are going to use the formula we derived earlier from trigonometry, that sigma d divided by 2 is equal to sigma m times sinus phi. Sigma m times sinus phi. So let's do that. Sigma d divided by 2, sigma m is here, sinus phi is there. One can solve for sigma 1 in a couple of steps, and one would obtain that sigma 1 is rho gy times 1 plus sinus phi divided by 1 minus sinus phi. If one does the same exercise in extension, one can solve this time not for sigma 1 because sigma 1 is known, is rho gy, but we solve for sigma 2. And sigma 2 is rho gy times 1 minus sinus phi divided by 1 plus sinus phi. So we have two expressions of sigma 1 and sigma 2. Now let's assume that phi is 30 degrees. This would simplify things quite a bit. It's a conservative estimate of the friction angle. So let's use 30 degrees. And one obtains that sigma 1 in compression is 3 times rho gy. And sigma 2 in extension is 1/3 of rho gy. So one can compute the pressure in compression. So the pressure in compression is sigma V plus sigma 1. Sigma 1 is 3 times rho gy plus rho gy divided by 2 times factor minus. So we have minus 2 times rho gy. This is what is called typically an overpressure, because the pressure here in compression would be 2 times larger than the lithostatic pressure. So this could have important effect on any pressure-dependent processes that takes place inside the Earth. Now in compression, we can compute the pressure also. It's 1/2 of the two values. Sigma 1 is 1/3 of rho gy, and sigma and the other stress is rho gy divided by 2. That makes minus 2/3 of rho gy. So here in extension we have an under pressure. The pressure predicted here is smaller than the lithostatic pressure. The same thing can be done to derive the differential stress in compression and in extension, and you will see that we obtain a similar estimate, except for the sign, for sigma d and p in compression or extension. So the differential stress and the pressure, they have a similar evolution with y, which is very interesting here. Let's remember the formula we've introduced beforehand, that sigma d divided by 2 is equal to sigma m times sinus phi. What one can do with this formula is to solve for the ratio of sigma d by sigma m, and this is equal to 2 times sinus phi. If phi is set to 30 degrees, then indeed sigma d divided by sigma m is equal to 1. So sigma d is equal to sigma m. So we have a coevolution. So that's very important because this tells you that the stress is different in compression and in extension, and that they evolve also with depths in a different way in compression and in extension. In the last lecture, we've discussed about elastic and viscous rheology of rocks and the deformation structure which are associated to this. And we've also discussed about frictional plasticity and faulting. What is important to remember from this lecture is that in the frictional behavior, we have a specificity. The strength and the pressure are different in extension or in compression. And they also evolve in a different manner with regard to depth. So on that part of the diagram, you see a representation of the differential stress. Here, difference between horizontal and vertical stress in extension versus the depth. And that part is for the compression. Let's first focus on that side. You see one line here in purple, and that's basically the differential stress for extension. So it's 2/3 of rho gy. That is this line here. In compression, you have a green line, and for this, the equation is different. It's 2 times rho gy. So we have two states of stress for compression and one for extension. So we've defined the frictional behavior. It's when the strength increases with pressure, and it's defined by these lines, which have different slopes in compression and extension. So for example, here you see the blue square is showing you the region in which frictional deformation can occur, down to this level here, down to that level in compression. And what is important is that in this regime, the fluid pressure can reduce the increase of stress with depth. So the slope of this line can be changed if you change the fluid pressure, basically. You can have different slopes here. But still, the behavior remains different in compression and extension. In the previous lecture, we discussed about viscous creep, and viscous creep is also represented on this diagram. And these are these lines or these curves that are featured at the base here. They show you a decrease of the differential stress with depth because temperature increases. You remember that in the viscous regime, when you increase the temperature, you have an exponential decay of the stress. That's what you see here. So on the top, you're brittle, and in the bottom, you're ductile or viscous. And that can be shown with this very simplified diagram, in which you have on one side extension, compression, and you see a brittle ductile transition that marks the transition between dominantly ductile to dominantly frictional regimes. And you see that the position of this transition is different in compression and in extension. And that is because the slope of the frictional criteria is different in compression and in extension. So faults or flexure are likely to happen in the colder part of the lithosphere, in the elastoplastic region here or there, while faults, necks, and channel flows are rather likely to take place under the brittle ductile transition. Of course, this is a very simplified view of the rheology of the lithosphere, and it may be much more complicated in reality, but this gives you already a little overview of what a brittle ductile transition is and how it relates to all the things we've discussed in this lecture. So as a conclusion, there are permanent deformations which are time independent, and these are the frictional plastic deformations that are basically manifested by the occurrence of a fault within the crust. They relate the differential stress to the pressure in the frictional plastic regime. The governing parameter is the friction angle. To represent the state of stress, we've used more diagrams, and we've been able to evaluate the angle of faults. Thus, we can also determine stable and unstable stress regime in the lithosphere. And we've also seen that a large portion of the lithosphere is governed by the frictional plastic rheology. And of course, it is dependent in extension and in compression. These are different. So thanks a lot for your attention.